Welcome, everyone, to the Nerd Werk Nexus. Can you believe it's been a whole century of quantum mechanics? What a ride it's been.
I know. It's mind-blowing to think about how much it's changed our understanding of how the universe works. And it all started with just a few scientists trying to figure out some weird experiments back in the 1920s.
Right. Like opening a door and finding a whole new world of physics behind it. So let's go back to 1925 for a second. What was happening in science back then?
Well, classical physics was the big thing back then. Newton's laws, Maxwell's equations, they seemed to explain pretty much everything. Planets moving, light behaving, it all fit. But then a few little problems started cropping up.
Problems? What color problems?
Well, one big one was about light. When you heat something up, it glows, right? And classical physics said that the energy from that glow should be spread out evenly across all the colors of light. But that's not what experiments showed.
Oh, so what did they see?
Instead of a smooth rainbow, they saw these distinct lines of color, like a fingerprint. Each element had its own unique pattern. It was a puzzle.
So the energy wasn't a smooth flow, more like it came in specific chunks.
Yeah, exactly, like steps on a staircase instead of a ramp. And that's where Max Planck comes in. He was trying to figure out this black body radiation, and he proposed this radical idea. What if energy isn't continuous? What if it comes in little packets? He called them quanta.
Quanta. That was a pretty big deal, right? Did everyone just suddenly agree with Planck?
Not quite. It took some time and a few more brilliant minds to really get the quantum revolution going. People like Heisenberg, Schrödinger, Born, they all brought their own unique ideas to the table.
Oh, yeah. Those are the big names in quantum mechanics. What did they do?
Well, Heisenberg, he came up with something called matrix mechanics. It was a whole new way of looking at how particles behave. It was pretty abstract, all about matrices and probability.
What about Schrödinger? Wasn't his approach a bit easier to understand?
Yeah, a lot of physicists found Schrödinger's wave mechanics more intuitive. He had this famous wave equation that described particles as waves, a really big shift from thinking of them as little points.
Wait, so particles are waves now.
Hmm.
But I thought we just said energy comes in little packets. How can something be a wave and a particle at the same time?
Well, that is the beauty and the weirdness of quantum mechanics. It challenges everything we thought we knew about reality. And it's not just some theory, we have experiments to prove it, like the double slit experiment.
The double slit experiment. That sounds interesting. Tell me more about that.
Okay, so imagine you have this wall with two tiny slits in it, and you start shooting electrons, those little particles, at the wall.
Okay, I'm picturing it. What happens?
Well, if electrons were just little balls, you'd expect them to go through one slit or the other and make two neat piles on the screen behind the wall.
Yeah, that makes sense.
But that's not what happens. Instead, you get this pattern of bright and dark bands on the screen, like waves interfering with each other.
Wait, seriously? So even though we're shooting single electrons, they're acting like waves and interfering with themselves?
Exactly. It's like each electron goes through both slits at the same time.
How is that even possible?
That's the million-dollar question. It gets even weirder. If you try to peek and see which slit the electron goes through, the interference pattern disappears. It's as if the act of observing it forces the electron to choose one path or the other.
Whoa, hold on. Are you saying our observation changes reality?
Well, it's not that straightforward. This is where the measurement problem comes in, and it's a real head-scratcher. But before we get too deep into that, let's talk about another big quantum idea, Heisenberg's uncertainty principle.
Oh yeah, Heisenberg. The one that says you can't know both the position and momentum of a particle with perfect accuracy.
Right. It's a fundamental limit. The more you know about one, the less you know about the other. It's like a cosmic balancing act.
So it's not just that our instruments aren't good enough. It's built into the universe itself.
Exactly. And this uncertainty is everywhere at the quantum level. Okay, so we've got these really strange concepts. Quanta, wave-particle duality, uncertainty. It's a lot to take in. But I bet not everyone was happy about this new quantum physics, right? Wasn't Einstein pretty skeptical?
Oh yeah, Einstein was not a fan of some of the implications of quantum mechanics, especially the idea that it was all about probabilities and chance. He famously said, God does not play dice.
He didn't like the randomness. What did he think was going on then?
Well, he believed there had to be a deeper explanation, a more complete theory that would get rid of all this uncertainty. He thought quantum mechanics was just a temporary fix, kind of like a blurry picture of a much clearer reality.
So he thought there was more to the story, something hidden beneath the quantum fuzziness.
Exactly. To be fair to Einstein, His skepticism actually led to some really interesting thought experiments like the EPR paradox.
EPR paradox, that rings a bell. Something to do with two entangled particles, right? Acting like they're connected no matter how far apart they are. That's the one. Spooky action at a distance, Einstein called it. It seemed to defy the rules of relativity.
Yeah, that does sound pretty spooky. What happened with that paradox?
It took a while, but eventually physicists came up with ways to test it experimentally. And guess what? Quantum mechanics was right. Entanglement is real, even if it seems impossible.
Wow, even Einstein got it wrong sometimes. So these early quantum pioneers really shook things up. But all this talk of wave functions and probabilities can get a bit abstract. What about the real world? Did quantum mechanics actually lead to any useful technology?
Oh, absolutely. In fact, much of the technology we use today wouldn't exist without quantum mechanics. Things like transistors, lasers, MRI machines, they all rely on quantum principles.
Wait, really? Those seem like pretty big leaps from these mind-bending theories. How did we get from abstract quantum ideas to transistors and lasers?
Well, take transistors. They're the tiny switches that make up all our electronics. Computers, phones, everything. And they work because of how electrons behave in semiconductors, which is a purely quantum phenomenon.
Okay, I see the connection with transistors. But lasers, those are beams of light, right? How are they connected to quantum mechanics?
Well, to make a laser, you need something called stimulated emission. It's when a photon of light hits an atom that's already excited and triggers it to release another identical photon. And that process, well, it's a quantum process.
So, understanding how light and matter interact at the quantum level is what made lasers possible. And you mentioned MRI machines, too.
Yeah. MRI uses powerful magnets to manipulate the spin of atomic nuclei, which is another quantum property. And that's how we get those detailed images of the inside of the body.
Wow, it's amazing how a theory that started with some weird experiments about glowing objects ended up leading to so much incredible technology.
It really shows the power of basic research, right? You never know where a fundamental discovery might lead.
And it seems like the quantum journey is far from over. There's still so much we don't know. Things like quantum gravity, the nature of time, the measurement problem. These are still big mysteries, aren't they?
Absolutely. These are the challenges that are keeping physicists up at night, trying to push quantum mechanics even further to answer the really big questions.
Okay, so let's talk about these mysteries then. What's the deal with quantum gravity? Why is it so hard to figure out? So quantum gravity, it's like we've got these two awesome theories, quantum mechanics for the tiny stuff, and general relativity for the big stuff, like gravity, but they just don't seem to get along.
Yeah, it's a real head-scratcher. Quantum mechanics is all about uncertainty and randomness, particles popping in and out of existence. But general relativity sees gravity as this smooth curvature in space-time. They're like speaking different languages.
So how do we even start to combine them?
Well, the problem is that our current understanding of gravity just doesn't work at the really small scales where quantum effects become important, like inside a black hole or the very beginning of the universe. We need a new theory, something that can handle both the quantum weirdness and the force of gravity.
A theory of everything.
That's the dream, a theory of quantum gravity. There are some promising ideas out there, like string theory.
String theory. That's the one with all the extra dimensions, right? Like way more than our usual three.
Yeah. It says that the fundamental building blocks of the universe aren't particles, but these tiny vibrating strings. And the different ways they vibrate give rise to all the different particles and forces, including gravity.
Okay, I'm trying to wrap my head around that. Vibrating strings in multiple dimensions. Pretty wild stuff. What about loop quantum gravity? I've heard that one mentioned too.
Right. Loop quantum gravity takes a different approach. It tries to quantize space-time itself, breaking it down into these tiny interconnected loops.
So string theory, with its extra dimensions, and loop quantum gravity with its space-time loops, it's like physics meets abstract art. But are there any experiments that can tell us which one is right?
That's the tough part. The energies and scales involved are just so extreme that testing these theories directly is a huge challenge. For now, it's mostly theoretical work, trying to see if these ideas make sense mathematically and if they lead to any predictions we could actually test.
So the search for quantum gravity continues. What about the nature of time? I've heard that quantum mechanics kind of messes with our usual idea of time as this arrow pointing from past to future.
It does. In classical physics, time is absolute. It ticks along at the same rate for everyone. But in quantum mechanics, it gets treated a bit differently. More like a background parameter, not something that's subject to quantum uncertainty.
So time is more flexible in quantum mechanics. Does that mean time travel might be possible after all?
Well, hold on. It's not that simple. While quantum mechanics does challenge our classical view of time, it doesn't necessarily mean we can hop into a time machine. It's more about how time is woven into the fabric of quantum theory.
Okay, so maybe no time travel just yet. What about that other big mystery? The measurement problem. The one where observing a quantum system seems to force it to choose a specific outcome.
Ah, yes, that's a real brain twister. You've got a quantum system in a superposition, meaning it's in all these possible states at once, but when you measure it, you only get one result. The wave function collapses.
Right, like the electron going through both slits until we try to see which one it actually went through. But what causes that collapse? Is it our consciousness?
That's a big question. Some interpretations of quantum mechanics say the observer is crucial. Others say the universe splits into multiple branches, with each branch representing a different outcome.
Whoa, multiple universes. That's a lot to process. So which interpretation is right?
Honestly, we don't know for sure yet. Each interpretation has its own strengths and weaknesses, and it's still a topic of debate.
So even after 100 years, quantum mechanics still has plenty of mysteries to solve.
Absolutely. It's a field that's constantly pushing the boundaries of knowledge, making us question what we thought we knew about reality.
Well, it's been an incredible journey exploring these quantum mysteries with you today.
It's been my pleasure.
From those early experiments to the amazing technologies we have today, quantum mechanics has come a long way. And who knows what incredible discoveries are still waiting out there.
The future of quantum is bright.
Absolutely. So, to all our fellow science enthusiasts listening, keep asking those big questions. Keep exploring the quantum world. It's a wild ride. Thanks for joining us here on the Nerd Werk Nexus.